Hey, let's take a look at section 4.3, rational inequalities and applications. So we have done inequalities before, right? We've done quadratic inequalities and we've just done polynomial inequalities, haven't we? So let's think about what we did for those. So with a polynomial inequality, like if we knew that the polynomial graph looked, something like this, right? We've got, here's y equal f of x. So if I wanted to solve f of x greater than or equal to 0 here, we can interpret this with the graph. So this is where is f of x above or on the x-axis, right? This was what we were asking. This was what this question right here was asking. Where is f of x bigger than or equal to 0? Well, if we want to know that, we can just appeal to the graph, right? So we see that this point, and this point are going to be our endpoints of our intervals that we have solutions, right? So for answering this question, we would just have, hey, between these two values are solutions and right of that value is a solution, right? So with polynomials, we had that the zeros were the only spot where these graphs can change sign. So remember when we did this, like if I had A, B, C, those are our zeros. We put them on a number line, right? And then we put test points between them, and we said, where is, sign of f, and then, test values. We did this stuff, and we did this in the last section too, didn't we? So yeah, these sign diagrams are what we're going to be up to in this section as well, right? So with polynomials, the only spots where the functions could change sign were at the zeros. But now we're talking about rational functions. So we have other options for where the functions can change sign. We might have seen something that looks, I don't know, like this in the previous section where maybe we had a horizontal asymptote. But we're going to have not just at zeros where this can change sign, but also at vertical asymptotes. So we need to worry about zeros, which are going to be, x-intercepts, which are going to be zeros of the numerator. And we're going to have these vertical asymptotes, which are zeros of the denominator. So really, we just need to find those zeros and make a sign diagram. We don't really need to think about the graph, and we don't really need to draw the graph in these cases. But it might be helpful to think about the graph. It might be helpful to draw it, but we certainly don't need to when we're just making these sign diagrams. So let's take care of this. All right, I saw that I had a typo there, so I fixed it. All right, so let's go for it. We want to let's maybe write some steps as we go. So to do this, first thing we're going to do, we're going to just kind of mimic the idea that we did with polynomials. So we want to get 0 on one side. So let's first let's write this as one fraction on one side, 0 on the other. Okay, so let's go for that. We got 2x cubed minus 4x plus 2 over x minus 1. And we're going to subtract these two terms. So we want minus x, and then minus negative 2 would be plus 2, right? All right, so we've got, when we add these together, we're going to need a common denominator, right? So to add these fractions, we need a common denominator. Well, it's x minus 1. So we multiply each of these terms by x minus 1 over x minus 1. That's a minus. And now we can combine the fractions because we have common denominator. Okay, so we've got 2x cubed minus 4x plus 2 in the numerator of this first one, and then we're going to subtract the new numerators here, right? So we've got minus x times x minus 1, and then plus 2 times x. It's all over the same denominator. Okay, great, greater than 0. All right, now we have a task here of combining like terms, simplify everything, right? So we got 2x cubed minus 4x plus 2, and then multiplying, we've got minus x squared minus x. It's going to be plus x, isn't it? Minus x times minus 1 plus. And then we got 2 times x And we've got 2 times -1, so -2. Okay. Yeah, we're just playing the simplification game here, right? Greater or equal to 0. Let's come up here because it's going to get a lot less messy in this step here. So combining like terms, our cube term doesn't have a like term with it. We got x squared is alone, and then what? Minus 4x plus 2, so that's minus 2x. And then we have 2. Oh, I guess I forgot about this x here. So we've got minus 2x plus x would be just minus x. And then we've got plus 2 minus 2, so that's 0. Okay, that just went away. All right, great. So we have it simplified in the numerator and the denominator, and we want to factor everything. So we can factor, x comes out of this term. Okay. And now we can factor that numerator further, can't we? So we would have 2x, we want minus and plus. And we can check ourselves, right? 2x squared minus 2x plus x, that gives us the minus x in the middle. Good. Okay, and we got x minus 1 greater or equal to 0. Okay, so now we're going to just put these zeros. Now we have, I guess that was our second step. So we wrote it as one fraction on one side, 0 on the other, then we factored everything. There we go. So our third step, we're going to put all zeros on a number line. And then we're going to find the sign of the rational function at test points between all of these. Okay, so let's do that. We've got our number line here, and we want to put all of the zeros of the numerator, oops, so all zeros of the numerator and all the zeros of the denominator. So what are those? Let's make a list. So zeros of numerator. We've got x equals 0, right? Comes from the first factor. X equal -1/2, that comes from the second factor. And then x equal 1, that comes from the third factor there. And the zeros of the numerator, or zeros of the denominator, we just have x equal 1. So these are going to be the only ones we're putting on here, right? So we got 0 on there, we got -1/2, we've got 1. Okay, notice something real quick here. If we would have multiplied at the very beginning to get rid of that denominator and make this thing a polynomial, we would not have added that to our list, right? So be careful with this because we want to preserve that as a 0. We want to keep this one with us, right? And even if we would take and cancel this out of the rational expression right there, we're going to get rid of that 0. We don't want to do that. We want to keep that 0, right? Okay. So now we're at the test point part. So we're going to have test points. Maybe let's pick -1. Let's pick -1/4. Let's pick 1/2. Let's pick 2. And we want the sign of the fraction. And I mean, let's just for simplicity's sake, let's call it f. And that way I don't have to write, the rational function. So sign of f, right? We want to write it as all one rational function. Okay, so now what we're going to do is we're just going to think about the sign of f of -1, right? So if we put a -1 in here, again, we only care about the sign. If I put a -1 in for x, that's going to be negative. If I put a -1 in on this term, that second one, that's going to be what? -2, it's going to be negative. The third one, that's going to be negative. And then the bottom one, that's going to be negative as well. So we have negative times negative, which is negative, divide by negative, which would end up being positive overall. So what we've shown is that on the graph, every point to the left of x equal 1/2 is going to be positive. Something that we didn't do here is we didn't put zeros here. That was a 0, that was a 0, and this was our question mark. That was a hole in the graph, remember? Okay, so now we're just plopping our test points out, right? So now we would think about x equal -1/4, and we can think about the sign of these factors, right? The first one in the top is going to be negative. The second one in the top, we're going to have -1/2 plus 1, so that's positive. And then we have -1/4 in that third one. We're going to have a negative there. And -1/4, we're going to have a negative there. So overall here, we're going to have negative times positive times negative in the numerator. So that would be negative. Excuse me, that would be positive. And then divided by a negative, that's going to be a negative number. Okay, and then we can think about what happens with the 1/2. So we put a 1/2 in there. Our first factor in the numerator is positive. Second factor also positive. Third factor, that one's going to be 1/2 minus 1, that's negative. And then 1/2 minus 1 is going to be negative. So that nets us a result of a positive number. Okay, and then we go on the other side of 1. Well, what's going to happen there? So I go to 2. So first factor is going to be positive. Second one's positive. Third one's positive. And the one on the bottom is positive, so they're all positive. Okay, so answering the question that we were asked was, where is this thing bigger than or equal to 0? Well, we just found it. It's all of these intervals here. This is all of these values for x are going to give us a positive number. All the numbers between here and here are going to be positive. This guy is going to give us an undefined number though, right? Because if we would put x equal 1 in there, that's not going to equal 0. That's going to be undefined, so we have to exclude that in this case, right? Think about what happened with the graph. When we canceled this factor out, that was a hole in the graph, right? So that's not equal, but there's going to be a hole. So technically, it's not going to be part of the solution set. And we can go ahead and give our answer as an x interval. So we got -infinity all the way to -1/2, bracket, union, 0 to 1, parentheses, union 1 to infinity. Okay, so yeah, it seemed like we wrote a whole lot, but the big idea here I don't think is so crazy. We're just finding all the potential x values for which a function can change sign. So let's do that again with, I guess, one here that's somewhat easier. Okay, so we're going to do the same thing, right? We're going to write it all on one side as one function, as one fraction. So to that end, let's subtract 3 from both sides, and we got 0. Now we want to add the fractions, so we need a common denominator, right? So 5x plus 4 over 5x plus 4. And move that 0 over here. Okay, and then we can multiply. So we got x minus 3 times 5x plus 4 over 5x plus 4 greater than 0. And we can multiply through. We got x minus 15x minus 12. Let's come up here. Okay, so now what? We've got negative 14x minus 12 over 5x plus 4 greater than 0. All right, so at this point, we want to factor everything, right? So we've got it written as one function, excuse me, one fraction, and it's we just want to write it in factored form. So we can do that. It looks kind of like it already is, right? And let's make a list of our zeros of the numerator and the zeros of the denominator. Okay, well, we're going to have to solve equations here, right? So we want negative 14x minus 12 equals 0. So that's going to say negative 14x equal 12. So we're going to have x equal 12 over 14 negative. So we're going to have x equal, simplifying that down, we got negative 6 over 7. Okay, now that's our 0 of the numerator. 0 of the denominator now, we're going to solve 5x plus 4 equals 0. So that's going to give us x equal negative 4/5. Probably didn't really need to do the work on that one. Okay, So now we're going to arrange these on a number line. So we can do that. We got 0 is here. Which one's bigger here, 4/5 or 6/7? I guess if we're wondering that, what might help us is if we would write them both with the same denominator, and then we can more clearly see which one's bigger. So if we write this as 35ths, I would multiply by 7/7, right? Times 7/7. So that would be negative 28 over 35. And if I multiply that by 5/5, we're going to have negative 30 over 25. So what that tells us is that negative 6/7 is further to the further to the left. Okay, so we're just arranging these things. 0 was not a 0. I don't know why I put that on there. So arranging these, we would have negative 6/7. We would have negative 4/5. And yeah, we want to pick our test points now. So pick easy stuff. So 0 is going to be over here. Negative 1 is going to be over here. And let's be a little tricky about this because we don't really need a test value in between. We only really need to use one test value. And let's think about what we did in previous sections here. So think about multiplicities of zeros. If we had, I know that we defined the word multiplicity using polynomials, but we can still use the word multiplicity when we're talking about zeros here because in the numerator it's a polynomial and in the denominator that it's a polynomial. So multiplicity is still a good word for us. So our multiplicity of this 0 here, multiplicity of that is 1, right? So that means that we're going to change sign at that 0. Remember that this is what happened with polynomials. When we had an odd multiplicity, our function changed sign. So we have multiplicity 1 for both of these zeros. So what that means is that it's going to change sign at both of those zeros, right? Because of the multiplicity. So really we only have to do one test point, right? So if I put 0 in there, that's going to be a negative number, right? And it's going to change sign at each of these zeros. So it's going to be positive in this region. It's going to be negative in this region. And that's great. So if that didn't make all that much sense, and if that didn't work for you, actually put these numbers in there and show yourself that it works. Find a number in there and actually do that. But as much as we can take shortcuts with things that we already know, we probably should, right? Because it makes our lives easier. What I did forget to do here is write that this was a 0 of the numerator. So I put a 0 there, and this is a 0 of the denominator. So I put a question mark there. So this means that if my inequality is a non-strict inequality, so if it were greater or equal, I would not include that point, right? But in this case, we're not going to include either one because we don't want the zeros, right? So we just want where this is bigger than 0. So we want strictly bigger. So we're going to have parentheses here, and we want everything in between. So we got negative 6/7 to negative 4/5 parentheses. And there's our solution set. A really common thing to do is to just find the zeros and just assume that it's all the things between them, but it's not. So we're going to need to use those sign diagrams or some other method to convince ourselves what we've got. Okay, good. Let's do one more. Same thing, right? We're going to get everything on one side first. And why don't we notice that, well, I guess it's probably easiest to just get everything on the left-hand side. So let's just do that. So we got negative x cubed plus 4x over x squared minus 9. And we see that, or we know that we're going to just have to multiply by x squared minus 9 over x squared minus 9 to combine the fractions, right? That's what we've been doing on these other ones. So now we're going to combine like terms in the numerator. Whoops, that's a cube. Okay, so then multiplying that through, we're going to have minus 4x cubed. And we're going to have plus 36x, right? Multiply, multiply. And then we've got that common denominator. Okay, so now what? We've got minus 5x, and that's cubed. And then I've got plus 40x over x squared minus 9. And we're still playing the, well, I guess that is simplified, but we should factor everything now. So let's take out a negative 5x from the numerator, and that's leaving us with x squared minus 9. Okay, and then we've got x squared minus 9 in the denominator as well. So our zeros here, well, I mean, we could probably see that the zeros are going to be plus and minus 3, but we technically didn't factor everything, and we can, you know. Great. So now we've got our zeros of the numerator. We got x equals 0 plus or minus 3, and we got zeros of the denominator, our x equal plus or minus 3, and now we're going to do our number line bit. All right, we do it. So our number line here, we've got negative 3, we've got 3, we got 0, and we can use our test points. So something, I guess, to notice now that I've said something about the multiplicity of zeros, we should notice something. When we're going through this 0 with our x values, so in particular here, we don't need to worry about it changing sign, because these cancel each other out and they don't really have an effect on the net result of the sign of the function, right? So what I mean by that is if this one's positive, that one's positive too. So positive over positive, that's positive. If I've got a negative, if this one's negative and this one's negative, well, they both have to be negative because they're the same thing, but negative divided by negative, that's positive. So we're not going to change sign at this one, and we're not going to change sign at this one, but we are going to change sign at that one. So, and again, if that doesn't work for us with our previous experience, that's fine, and we can absolutely put test points in there, choose easy values, and we can plug these numbers in there, right? If I put in negative 4, and we think about what the sign of this thing is, we would have that first factor here would be positive, and then everything else is going to cancel out, isn't it? So we're just going to have a positive. And then if I put a negative 1 in there, we're going to have a positive for that first factor, and then everything else is going to cancel itself out. And then if I put the 0, passing through 0, I go to a positive 1. That factor is going to be negative now, and everything else cancels out. Again, every time, everything cancels out with those, right? I put in 4, we're going to have a negative number. Everything cancels out here. Now, the only thing we got to worry about here is whether these are zeros of the denominator, and these are zeros of the denominator, so we can't have these two values as solutions because we are a non-strict inequality. So we do want that one. So we want this number here and everywhere else that it's positive. So that's all the numbers over here excluding negative 3. We go all the way over here. And there we go. We have our interval. We'll make a little bracket there. So we've got negative infinity all the way to negative 3, and then union. What's a union? Not a 0. Negative 3 all the way to 0, including 0. All right, super. So yeah, we just find we write it all as one fraction on one side of the equation. We factor everything, and then we make our little sign diagram. And we can, absolutely use test points if we need to do that, and we probably should. But we can also think about what's going to happen based on our previous experience, right? We know stuff about multiplicities, and we know things about the way fractions work in general. The things to be careful about here are whether or not we're talking about zeros of the denominator, and those are going to be needing to exclude those from our solution sets. Okay, good. Now we have application problems, the dreaded application problem. So yeah, application problems. So with most of these, we want to do the same strategy every time. So we read the problem, we understand what they're asking, and we write some math stuff, translate the problem into a math equation, and then solve it, right? So with certain classes of these, it's going to be much easier for us if we make a little chart. And when I mean certain classes of these, I mean specifically the things that we have a little formula for. So Carl and Mike here are racing. They're going to have both have a distance, a rate, and a time, right? We know that the way that those are related is that distance is equal to rate times time. And whenever we have something in a fixed relationship, we ought to organize ourselves in a chart because it's easier. So let's do that here. So we've got Carl here, and we've got Mike here. They're both going to have a distance. They're both going to have a rate. They're both going to have a time. We can make a little chart. What a beautiful chart. Okay, so Mike ran the race at 6 miles per hour. So that's Mike's rate. So 6 miles per hour. And he finishes 10 minutes before Carl. How fast does Carl run? Okay, well, let's fill in the other stuff. So distance, they're both going to be 3 miles, right? Rate. How fast does Carl run? Well, that's what we want. Let's say Carl runs X miles per hour. Okay, so Carl's rate is X. Well, now we want to know what do we put here and what do we put here, right? Because we don't know. We know that Mike finishes 10 minutes before Carl, so Mike's time is 10 minutes less than Carl. Okay. Carl's time. Okay, well, what we're going to do is we're going to use this, right? We have two distances, we have two rates. Why don't we just rearrange this to give us a time, right? If we divide both sides by r, we're going to have distance over rate equals time, right? So distance over rate, we got 3 over x. Distance over rate for Mike, we've got 3 over 6, when that's a half. And these are hours, right? Important. Okay. So now what? We can use what we've written here, right? Mike's time is 10 minutes less than Carl's. So Mike's time, well, that's half hour, that means equals 10 minutes less than Carl's. So less than Carl's. So Carl's time, take away 10 minutes. Well, we got hours over here, minutes over here, so we need hours, right? 10 minutes, that's 1/6 of an hour, isn't it? And we can convert that, right? There's 60 minutes in an hour, or 1 hour is 60 minutes. And that means that 1/6 of an hour is 10 minutes, right? Divide by 60. Okay, cool. So we know that. All right. So now, lo and behold, we have an equation and we can solve it, right? So we've got 1/2 equal 3 over x minus 1 over 6. So we can solve this, and we usually solve these in the same way every time. We want to just, I guess, get rid of the fractions would be the easiest thing to do. And in the context of this problem, it does not make any sense at all for Carl to be running 0 miles per hour. So we know that Carl is not running 0 miles per hour. And in particular, we can multiply by x on both sides. If we want to get rid of all the fractions, we can multiply everything by 6x. Maybe we should just note x can't be 0 since we did that, right? So multiplying all of these through, we would have 6 divided by 2, that's 3x. And then we multiply it through by 6x to both of these terms. So we're going to have 18. And then this one's going to be just x. And now we play the solve for x game. So let's add x to both sides. We've got 4x equal 18. And then we have x equal 18 over 4, which is 9 over 2. And we've got to slap a unit on there. We were dealing with rate, right? This is miles per hour. So x is miles per hour, 9.2, or excuse me, 9 over 2 miles per hour. So that's 4.5, right? 4.5 miles per hour. Yeah, I only write 4.5 because it's not like we're going to go say to someone, we're not going to say to our friend, you know, Carl's running 9 halves of a mile per hour. We're going to say 4.5 miles per hour. Okay, super. So, is this reasonable? That's another thing we need to do is we need to ask ourselves, is this reasonable at the end? So, is it reasonable for a man or for a guy to run 4.5 miles an hour? I think it is, especially if Mike runs 6 miles per hour, right? And further, if Mike finishes the race before Carl, Carl ought to be running slower than Mike, which we found that he did. We could also go and determine how fast he would run the race using our original little distances rate times time and see, hey, is that actually 10 minutes faster? But we can do that, and I would leave that to you. I would very much encourage you to convince yourself that this is a reasonable solution. Okay, good. All right. So with both of these next ones, we're going to use the same idea. If I have two rates that are working together, if I add them together, we're going to get the total rate. So think about if you're running, right? If I'm running in this direction and the wind is blowing at my back, what's the wind going to do to my speed? It's going to add to my speed, right? It's going to make me go faster. And think about also maybe if I'm running, what's the wind against me going to do? Well, the wind against you is going to work against you, so it's going to be subtracted from yours, right? So I don't know. That's pretty hand wavy. Essentially, the idea is that our first rate plus our second rate is our total rate. And it could be that they're working against each other, and we would express that with a negative unit, as we'll see in this problem here. So we've got a faucet can fill a sink in 5 minutes, and a drain is going to empty the same sink in 8 minutes. Okay, so if the faucet is turned on and the drain is left open, how long will it take to fill the sink? Well, let's first ask ourselves, is it going to fill the sink? Because if we don't have to do anything, then we just say, hey, it's not going to fill the sink because of blah, blah, blah. Okay, so if the sink can be filled by the faucet in 5 minutes, and it will empty a whole sink, the drain empties a whole sink in 8 minutes, then yeah, it's going to fill faster than it's going to drain. So it is going to fill up the sink. So we ought to think about that first before we even start and say, hey, is this even a reasonable question to ask? Because if these numbers were switched, then it would drain faster than it would fill. So it wouldn't fill, right? All right, anyway, let's figure this out. So we got rate 1, so faucet rate plus drain rate equals total rate. Okay, so rate. When we're talking about rate, what is it that we're talking about? We're talking about fills a sink in 5 minutes. So that's one sink per 5 minutes, right? Sinks per minute, one sink per minute. And if I talk about my drain rate, it's going to empty the same sink. So minus one sink, right? It's going to take a whole sink of water away in 8 minutes. Okay, and then I want my total rate. I want one sink per unit of time, X minutes, right? And we can deal with this. So writing this in a little better way, we got 1/5 plus, well, we can just write minus 1/8, can't we? Equals 1 over x. And now we've got something that we can solve relatively quickly here too, can't we? If we write 1/5 as with a common denominator here, 5 and 8, the common denominator there, they don't have any common factors, so it's just going to be the product of the two of them. So we're going to have 8 over 40 minus 5 over 40 equals 1 over x. Take that up there. So we got 3 over 40 equals 1 over x. Now we just take reciprocals. So we got x has to be 40 over 3. And this would be sinks. Or excuse me, no. We got to remember what the variable was. This was minutes, right? So x minutes. So 40 over 3 minutes. So, and again, we're probably not going to go say to our friend, hey, it's going to fill the sink in 40 over 3 minutes. We're going to say 13 and a third, right? So 13.3 repeating minutes. We can write that if we want to, or we could write it as 13 plus 1/3, or we could just say about 13 minutes. That's probably fine too. But this is what's going to be preferred, right? Because we're not using our calculators, and we can do 40 over 3 and just leave it like that. But we do, got to remember the units, and that's going to be troublesome for us sometimes. Okay, wonderful. We got one more. Oh look, Daniel and Donnie cleaning a llama pen. They have joint ownership of a llama, and they are cleaning the pen, and they both do it together in 45 minutes. That's great. Daniel cleans the pen in 1 hour. All right, and we want to know how long it takes Donnie to clean it alone. Okay, so we're going to do the same thing, right? Rate 1 plus rate 2 equals our total rate. Okay, so Daniel and Donnie clean it together. So they do 1 pen in 45 minutes. All right, Daniel cleans the pen alone in 1 hour. So let's call Daniel rate 1. So that's 1 pen. And we can see right away that we need to have this in minutes. So let's write that in minutes. 1 hour is 60 minutes, isn't it? And what we want is Donnie's rate, 1 pen per how many minutes? I don't know. So let me write that just to be totally clear here. We're going to say that this is Dan and this is Donnie's, and then this is together. And now we have a wonderful equation that we can solve that relates their rates, and we can sure as heck solve this. So yeah, let's go ahead and do that. Let me write this real quick. Okay, so let's add the fractions together. We can use various strategies here, and when we're having to do these calculations by hand, it might not be as easy as we want it to be to find the least common denominator. So I mean, we might add the fractions together here. I guess what I'm trying to say is there are many ways that we can solve these things, and pick the one that works the best for you. In my mind here, it's going to work easier for me if I just add the fraction together and go from there. So let's do it. So yeah, adding these together, we're going to multiply that by x over x, multiply this one by 60 over 60. So we've got x plus 60 over 60x equal 1 over 45. And now I've got reciprocals here, so I can just flip both fractions over. And now we can multiply both sides by x plus 60 to get rid of that. And maybe come up here. That's separate. So now what? We've got 60x equals 45x. And then what? 60 times 45. What's that? We have a 27. And then, okay. I'm going to rewrite that on a below instead. Okay, there we go. So on the left side, those cancel out. We just have 60x. And on the right side, we have 45x plus 2700. Right, and we can do 45 times 60, right? And then what? We can subtract from both sides. We have 15x equal 2700. And then solving for x, we got 2700 over 15. And now we can reduce this. So we remember our units. We got 180 minutes. And, if we wanted to write that as hours, we could say that that's 3 hours. Okay, so is this reasonable? If the one guy, I put the problem down here. So if they do it together in 45 minutes and on his own, Daniel can clean it in an hour. If Daniel works alone, he can do this thing in an hour. And if they work together, they do it in 45 minutes. So Donnie can't be doing that fast, right? Because he doesn't really improve Daniel's time by that much. 15 minutes really isn't all that much. So Donnie's probably going to be pretty slow at it, or at least not as fast as Donnie or Daniel, right? They're 2 D names. What a great alliteration. And anyway, we should expect Donnie to be considerably slower, or at least a little bit slower than Daniel. And it turned out that he was slower than Daniel, and this is reasonable, right? 3 hours. So yeah, we can do it. We've got rational inequalities, and we can also solve application problems. So yeah, that's it. So thanks for watching the video, and yeah, have a great rest of your day.